Welcome back to the Inclusive Mathematics Professional Development Series. Our third module is on mathematical methods, how we can use inclusive pedagogy and practices to support all learners. By the end of this module, you should have an understanding of the research foundations of both special education and general education pedagogies and methods for teaching mathematics. You will be able to describe ways instructional approaches may differ depending on the pedagogy selected and the goals of the instruction. Throughout the module, I also hope you will reflect on how your current instruction may or may not promote inclusive math instruction and identify some ways to grow. Before we dive in, take a moment to pause the video and reflect on what you think when you hear the words inclusive math instruction. What does it look like? What doesn't it look like? Can you give examples from your own experience? Pause now to jot down some ideas. Let's begin by examining some educational research focused on special education, which I also refer to as inclusive education. There are many ways you can learn about research-based methods for teaching mathematics to learners with disabilities. For example, the organization Council for Exceptional Children publishes research-based instructional materials in a variety of formats. They sponsor several academic journals. For teachers, a great journal to read is Teaching Exceptional Children. This journal is written with a teacher practitioner as the primary audience target. For an overview of research-based math instruction that promotes inclusion, one of my favorite articles is by Dobler and colleagues, who are prominent researchers in math for learners with disabilities. Dobler and colleagues synthesized findings for decades of math research into these 8 guidelines that should be considered during core or Tier 1 math instruction. The first guideline is to prioritize instruction around the critical content. If you look at a lesson plan in the teacher manual for any curriculum, you'll often see so much content crammed into one lesson. Curriculum developers try to give you tips for differentiation and tend to give you more content than you can realistically fit into one lesson. It is your job to sort through it, consider the needs of your specific students, and prioritize the critical content first. How do you figure out what the critical content is, though? You first look to the lesson objective and the focus standards of the lesson. Ask yourself, what skills must the student do independently by the end of this lesson? Then think more broadly and consider where this fits into the math unit and the scope and sequence for the entire year. Focus your instruction on the critical skills first and save all those extras for differentiation as needed. I also like to set differentiated lesson goals for my students. This is an example of differentiated lesson goals for a second grade measurement unit. Let's say the focus standard involves selecting and using appropriate tools such as rulers, yardsticks, meter sticks, and measuring tapes. By the end of this particular lesson, I want my students to be able to select an appropriate measuring tool and the units based on the size of the object. So maybe a student selects to measure a pencil in inches, the length of a table in feet, and the length of a room in yards. All students should be able to verbally justify those choices because that is the critical content of the lesson. Now, some students may also have time to integrate writing into the lesson and may write their justification out as well. And then a few students may even take that a step further and select multiple units and compare and contrast the benefits of using each. Having these differentiated goals are a great way to help organize all of the content in a given lesson, so the foundational tier becomes for all students, and that is your critical content. Before teaching any lesson, you must identify what prerequisite skills your students must have to be successful with the new content of the lesson. For example, a student must be able to count with one-to-one correspondence before using manipulatives to add factors and find their sum. Let's imagine you're teaching a lesson on multi-digit subtraction, and you have a student who is struggling with basic subtraction within 10. You may want to begin the lesson with some whole or small group explicit review of basic subtraction facts first, as a warm-up for everyone. Then you can document which students have difficulty with those prerequisite skills. Perhaps the difficulties show a need for using manipulatives for those students, or having other accommodations like number lines or 100 grids. These instructional aids can be used so the teacher is not stopping mid-lesson for everybody else if only 1 or 2 students are struggling. You don't want to stop in the middle of the critical content part of the lesson to review spontaneously, because that tends not to be helpful for anyone. Those students might require more intensive explicit instruction at another time during designated Tier 2 support time. So your job in these situations is to be as proactive as you can with a quick review to start lessons and including supports to offload those prerequisite skills so that during the lesson they can focus on the critical content. You can also utilize your co-teachers or paraprofessionals if you have them to help practice prerequisite concepts before a lesson. And if you plan to use instructional or assistive technology to offload lower order skills like basic math facts during those lessons, you still need to make sure you teach the students how to use those tools for learning. The third guideline is extremely important. I can't tell you how many times I look at the instructional materials like worksheets that go along with a lesson and think, why did they just throw this tricky one in the middle here? Students need ample time to practice simple examples that follow the basic procedural rules before you throw in unique cases. The sequence of examples is important for modeling, guided practice, and independent practice. Look at the order on this slide. They are all 4-digit minus 3-digit subtraction expressions. But notice how the first example on the left will not require any regrouping when using the US standard algorithm. The middle example will require some regrouping using that standard method, and the last, which has subtraction across zeros, is the most complex, and it will require regrouping across multiple place values. You should check the lesson and all the materials, including potential homework, to see that the examples begin simple and end more complex. You need to include both examples and non-examples in your lessons and use that as a teaching opportunity. And you should only assign independent practice if you have sufficiently modeled and practiced similar examples together in class. All of these things might require altering worksheets or just selecting different practice materials. Don't just use the homework sheet or the practice worksheet because it came with the lesson. Throughout this series, you will hear me talk about instructional scaffolds. Explicit instruction, for example, is one type of scaffold. It involves the gradual release from the teacher modeling, then to guided and supported practice, and eventually all that support is backed off to student independence with the skill. Scaffolds are any temporary support to give students the help they need to become more independent with the skill. Think about the scaffolds on a building during a construction process. They're not meant to stay there permanently. They only offer support during the construction process. In education, these might include things like breaking down complex skills, providing hints and reminders, using manipulatives, and generating visual representations of concepts. These don't stay there the whole time, but are there during the learning process. Many math programs will rely on students discovering mathematical connections through inquiry, problem-based instruction. More on this instructional approach shortly. It is very important for students to make these connections, but for our at-risk learners or those whose learning may be impacted by disabilities, they may not make all the connections on their own without support. You can help them make mathematical connections by using think-alouds to model mathematical thinking. When supporting them during independent practice, ask probing questions or model similar problems rather than just telling them what to do next. We'll dive into mathematical modeling more in a later video of this series. Practice and review should be cumulative and distributed. This means you can't teach math topics in discrete units. You must regularly spiral your curriculum and revisit content throughout the year so students are given the opportunity to review, apply, and generalize prerequisite skills and concepts. Be wary of your questioning strategies. Posing broad questions to the class often results in quick responses from the same few students. Rather than posing a question and calling on a student with a raised hand, try to incorporate active learning practices that allow all students to respond and interact with content. And when you do pose a question, give sufficient wait time. Sometimes students aren't engaging with content because you are not offering them the opportunity to do so. Visuals are helpful for understanding complex concepts in math, and it is one of the reasons why we use manipulatives in our instruction. Most math programs today use non-traditional representations to try to address the push for multiple representations and methods that exist in the Common Core standards. Some of the visuals really push students and teachers to think outside the box. My advice to you is to make sure you understand the visual before you teach it. This may sound obvious, but I've seen way too many teachers try to teach something just because it's part of the curriculum. But their misconceptions actually led them to teaching it incorrectly or not being able to support their students when they have questions. If students practice incorrectly, this will lead to misconceptions. Timely feedback needs to be specific, and it should include both affirmative and corrective feedback. In fact, the ability to incorporate immediate feedback is one of the features I look for in the technology I select for teaching. Another place you can find research-supported practices and approaches to teaching learners with disabilities is through the resources linked on the High Leverage Practices in Special Education website. I'm not going to go over these in depth because there are 22 HLPs, and I could do a whole series on just these. The HLPs are centered around 4 areas: collaboration, assessment, social-emotional behavior, and instruction. If you look closely at the instruction HLPs, you'll notice significant overlap with the 8 guidelines I just presented from Dobler and colleagues. This is because these resources I'm drawing your attention to are syntheses of many research studies conducted with many learners in many different settings and subjects over the years. It's important for you to understand that the research in special education methods and practices is largely based in quantitative research methods and behaviorist pedagogy. Researchers have aimed to operationally define an observable notion of what learning is, and then they measure the impact of certain practices. This is what we do on IEPs as well. I bring this up because as we dive a little deeper into math practices, you will be able to see why there's some disconnect and difference in special education approaches and general education approaches to teaching math. Because we don't have time to go into all the HLPs, I'll illustrate my point about special ed versus general education methods by focusing on 3 of the instructional HLPs, 11, 12, and 13, which are all about identifying and prioritizing long and short-term learning goals, kind of like Dobler's emphasis on critical content. Number 12 focuses on systematically designing instruction toward a specific learning goal. And finally, number 13 is about adapting curriculum tasks and materials for those goals, understanding that not everyone will take the same path to the goals. Special education research methods and practices are well suited for these narrow learning goals. Like in this example, students in first grade are asked to measure objects using non-standard units and express the length of the object as a whole number of length units. In this picture, the pencil is 6 paper clips long. I could use the HLPs and many of Dobler's guidelines to think about the prerequisite skills and knowledge needed for reaching the long-term goal of this standard, and then systematically designing instruction and adapting tasks to help all of my learners achieve this goal. For example, in order to measure with paper clips, students need to have one-to-one correspondence so they're able to count objects like paper clips. They also need to have some conceptual understanding that they need to use the same size object when measuring, or we will not have reliable measurements. Again, the 8 guidelines and the HLPs are wonderful for helping us target these narrow learning goals like this. Narrow, meaning they are very specific and observable, and they could be measurable in a single lesson. But what happens when learning goals aren't so narrowly defined? In math and other STEM subjects in particular, many of our learning goals are much broader. Those standards for mathematical practice that I introduced in the first module of this series are much broader learning goals. These practices are developed over years and demonstrated in multiple ways. There is never really the opportunity to say they are mastered like our narrow learning goals. This is where general education and special education math practices tend to differ. The approaches, methods, and pedagogy we select for teaching can be thought of as a spectrum. On the left-hand side of this spectrum are our more teacher-driven approaches, which are most often researched in special education. Notice I said teacher-driven and not teacher-centered. Sometimes people falsely characterize direct, explicit approaches as being teacher-centered, but in reality, all good teaching is student-centered. Teacher-driven approaches are simply using the teacher's expertise in assessing student needs to carefully scaffold learning toward the learning goal. On the right-hand side of the spectrum are our more student-driven approaches, where students ask the questions and they develop their own methods for answering them. In an ideal world, all lessons would fall on the right side of the spectrum, authentic learning, where our learners wonder about things and craft their own problems, experiments, or tasks, and then work collaboratively to research and solve them. That's not a reality, though. We need to consider our learners, the tasks, and the instructional goals and purposes when choosing a pedagogical approach to teaching. The more teacher-driven approaches are best for novices in the content, for younger students, and students with higher support needs. Whereas the more student-driven approaches are great for those who are approaching expertise in their knowledge of the content, older students, or those with lower support needs. General education research on math instruction tends to fall more on the right side of the spectrum because mathematicians recognize the messiness of real-world math. No one will ever just hand you a worksheet of problems in isolated skill sets, so we need to find ways to support learning in a real-world context. A lot of general education research is qualitative in nature, as researchers investigate unique ways in which students engage with mathematics and construct their math knowledge. This accounts for some of that disconnect between general education and special education math instructional approaches. So where should math instruction fall? Where does your curriculum fall in this spectrum? Where do you feel most comfortable teaching? There's no right answer here. Inclusive practices are those that have high expectations and push students toward the right side of the spectrum as they're ready, but not forgetting about the need for explicit approaches when targeting narrow learning skills and providing the support they need. Regardless of where your comfort zone is and the approach taken by your curriculum, it's important for you to maintain flexibility and balance in the approach you take if you want your math instruction to truly be inclusive. It all comes down to the purpose and goals of the lesson and the needs of our learners. Sometimes you might start a lesson explicitly, and then you realize the students are grasping the content sooner than you thought. You should be ready with extension activities and tasks that will challenge their thinking and push them toward the right on this spectrum. Likewise, you might start with a rich mathematical problem or task that you want students to work together on. But then you quickly realize that there are prerequisite knowledge gaps in most students that are presenting a barrier to their learning. At that point, you may want to pause the task and do some explicit instruction or review, moving left on the spectrum, and then approach that task another day. Let's review this spectrum and how to find balance using one of my favorite analogies. Imagine your classroom is a wide open pasture for learning, and your students are the sheep in this image. Notice how those sheep are clustered or isolated even in different parts of this pasture. This represents the diverse abilities and interests of our students in our class. Here we have an example of a narrow learning target, a small opening in the fence to corral our students through. This example of factoring trinomials is narrow because there's really only one right way to factor a trinomial, though different strategies may be used to get to that answer. You could use explicit instruction, which falls more on the left side of the spectrum, to carefully model for students, then give them time to practice with you slowly taking away your support, and then independently demonstrating to you that they have acquired the skill. Even if this takes place over multiple lessons and different students reach that goal at different times, this explicit approach focuses on mastery learning for all students. I do want to mention an inclusion warning with this approach, though. If you only use explicit approaches, math could lose meaning and purpose. If math is always absent of real-life content and you always sort math problems of similar types together, will your students be able to generalize their knowledge and know what to do if they encounter this scenario in real life? With explicit instruction, it's easy to overemphasize procedures and memorization over mathematical thinking, so you have to be careful. Let's look at an example that's more appropriate for problem-based or inquiry learning, which falls more on the right side of the spectrum. In this example, we have a fairly wide learning goal of designing a building that meets specific criteria. Perhaps it has specific area for storage, certain number of rooms, windows, doors, etc. And then they have to stay within a budget. This is going to require a wide range of math skills. It will also have multiple right approaches and multiple right answers. This is an example of the messy real-world math that is often targeted in general education math research. It's a great way to give math meaning and to bring student choice into the lesson. But all pedagogical approaches come with inclusion warnings. In this constructivist, inquiry-based, and problem-based approach, student outcomes may be less predictable. It's also easy to have some students feeling lost or confused if their errors are not caught, and they effectively are reinforced if the teacher does not intervene in time. So where does this leave us? You can add instructional scaffolds like guideposts to help students toward the goal when you use problem-based and inquiry learning. You can have visual representations and support sheets for the prerequisite skills required for the task. If you monitor students closely, you can intervene at the right moments and provide timely feedback to steer them in the right direction. You can provide explicit mini lessons to some students in groups as needed while other groups are working, so you're not holding anyone back and still providing support as needed. You can even adapt the task so different groups have more or fewer criteria to address. We'll see some examples of this in an upcoming module in the series. I'd like to close this module bringing us back to our mantra that all students can think mathematically. You've seen a few times where I say, no tricks to circumvent the thinking, and instead use scaffolds to support the thinking. When I say tricks, I mean those cute little sayings, visuals, or shortcuts that might help a student solve the problem in front of them, but they're really absent of mathematical conceptual understanding. These tricks may help in the short term, but they will not help students generalize and will harm them in the long run. See more of these tricks to avoid at nixthetricks.com. Instead of tricks, we can provide instructional scaffolds, which need to be provided over time. These are not shortcuts, but instead, they support mathematical thinking. Some examples of scaffolds are on this slide. How many of these scaffolds are things you use on a regular basis with your students? To extend your understanding of this content, I invite you to reflect on your biggest takeaways from this module and what you can apply right away. Look at the next unit in your math curriculum. What pedagogical approaches are used? What kind of learning goals are there? Are they narrow? Are they wide? Is it a mix? What are the prerequisite skills students will need? Where do you see the potential to be more flexible in the way you teach the content so you can find a balance between mastery of narrow skills and authentic, meaningful math application?